Yeah, thank you so much for the introduction, and also thank you so much for the invitation. And hello all. This is my really the first online, not online, and offline in-person talk in the last past years. And speaking of psychiatrists, honestly, I'm rather afraid of them because they usually ask me diagnosis-related questions. Usually, I don't have the answer yet. But let's see if I can try to convince you something about flexible behavior in autism spectrum disorders, and with a slight focus on Bayesian modeling. So this is the practical part in this part of the talk. So I'm Lei, as Florian said, introduced. So I'm a postdoc at the Scan Unit in Vienna. And let's see. Today we will be talking about flexible behavior. And this fits, I will explain to you why this fits into the theme of change of the Spring School. And then I will be talking about modeling flexible behavior in autism as one example. Then I will talk a little bit about computational psychiatry because the example I will be giving you in here is an excellent example of computational psychiatry. So I will just try to kind of slightly introduce this new field to you because this field is rather new, maybe just less than 10 years old, but I think it is interesting and exciting. So if you are doing some study with this focus for your future career, that can be quite insightful and exciting, I guess. Then lastly, I will be talking to you a bit about the age-based EM package, because the idea is that running computational models, especially the Bayesian models, can be a little bit tricky to begin with, especially if you are a beginner. So we, a few years ago, developed a package, and here I will be showing you slightly how that works. Right, so flexible behavior and how can that be related to the theme of this spring school. So I went online this morning when I was on the train from Vienna to Graz. So I found this one. It is really a nice picture and also the theme regarding why we are here, right? We are interested in change and how to measure, detect, and quantify changes reliably. So I will, in my part of the talk, I will mainly talk about detect and quantify. It's in a way that there are changes in the environments, and people usually have to respond accordingly. So if there's a change, you will detect the change as individual, and then your behavior will also change accordingly. This is indeed already called the flexible behavior. So let's see how the kind of introduction or definition of flexible behavior. That's essentially means that there are multiple meanings, of course, but essentially the core part, if you look at different definitions, the overlapping part is that there will be inflexible behavior if individuals behave flexibly. That means people will have adaptive change of behavior in response to the changing environment contingencies. As I said, if there's a change of the environment, will you be able to detect that change? And then will you be able to adapt your behavior accordingly, given that change in the environment? So as one example, when it is sunny, people tend to go outside, and when it is rainy, people just go inside, or people have to bring their umbrella if they have to walk in the street. And like another example is before COVID, and people teach online usually, and when COVID happened, people switch quickly to online teaching. So when the environment changes, there is always a contingency to change the according behavior. But today is different. Today is sunny, and we are doing kind of online hybrid teaching, but inside. So to investigate flexible behavior experimentally, there are also many paradigms. But one paradigm that we are interested in, or we focused on, we have used in the past, is something called a probabilistic reversal learning paradigm. So essentially, this is an associative learning task where individuals will see two icons or symbols, and each of them, they will give you reward with a probability. So for example, there are two reward, two choice options, and A and B, blue and yellow. So if you choose A, 80% of the time you will get a reward, 20% of the time you get a punishment. The reverse is option B. If you choose B multiple times, 20% of the time you get a reward, and 80% of the time you get a loss. So you know, I told you now, right? You know which is better, which is worse. You choose A over B most of the time. But what if you don't know? You will just have to press, make a choice, and see what outcome, what feedback you obtain, and then using that feedback, you are trying to learn the underlying probability of them. This is not reversal yet. So what is reversal? Reversal essentially basically means there's a change, right? So 80-20 here becomes 20-80, and then this one also. So that means the better option will become worse, and then the worse option will become better. So this is the change of the environment. So if I'm telling you, hey, do a choice task, there are A and B, you have to choose which one you think will give you the maximum award at the end of the experiment. You do this 100 times, for instance. You don't know whether there will be the change if there is the change, when the change will happen. If you don't know that, you will have to repeatedly make the choice. Choose A, then see the outcome, choose B, see the outcome, choose A, then see the outcome. And then there will be a moment you find out, maybe there's a change in the environment, so the reversal happens, and then you will change your behavior accordingly. This is what we will be measuring. If you understand how the task works, then you will also quite easily follow what will be the measurement, right? What can be measured in this task is if there is a vertical line before the reversal, how often do people choose option A because A is the better one? And after the reversal, how often do people choose option B because B is the better one? So the accuracy in both phases, acquisition phase, learning phase, and the reversal phase. And then we could also think about after the reversal, because I didn't tell you the reversal when that will happen, but you will use your choice and the corresponding feedback to educate yourself, to learn when the environment has changed. But at some point, you could also imagine, well, maybe people didn't really learn this very well, and they will still, after the reversal, they will still choose the previously better one. So those are the mistakes. So here, to count how often people make the mistake after the reversal is also an interesting measurement. I didn't talk about modeling yet, so those are kind of the classic traditional approach of analyzing the task. How does modeling come to play? So we actually this task is essentially very suitable for computational modeling, to apply some modeling technique and framework to analyze the behavioral data. And also putting that into a framework. So here we kind of focus on some learning theories, and based on the learning theory, we are interested in, given that learning model, what can we apply? How can we apply a learning model to the current task so that we could apply theory-driven computational approach to solve the task in a different perspective? And in fact, theory-driven computational modeling approach is getting a lot increasingly popular in kind of neuroscience, psychology, and there is a recent piece from January this year, 2 months ago, in articulating the idea to use computational model to build better theories. So also like related to the first talk before me, there can be the transition from oral model, which describe it using words, to mathematical equations and formulations, so that we can test it, also verify that if the model doesn't work well as we expected. Right, so then computational modeling in terms of cognition, essentially that defines cognition as information processing. There's some input, there's some output. This is very vague, just a regular function, doesn't really say anything. And in terms of behavior, it turns out that in as early as 1930s, like psychologist Kurt Lewin, and it's also very, very vague, honestly, but here, instead of just very arbitrary input-output, he used kind of a formulation to explain behavior as a function of the person and also the environment. You can think that as kind of a input factor and internal factor and external factor to explain the behavior of individuals. This is just a rough idea. I will later show you one example using a task in autism. So autism spectrum disorder, as you probably know, there are many symptoms, and two of the main symptoms of autism spectrum disorder are social communication deficit and repetitive behavior. Usually from the media or maybe from your classic textbook, we talk about the social communication deficits and autism. But actually, another one, this is also quite rather major. That is the repetitive behavior. So we are focusing on the repetitive behavior here. In our example, we are focusing on that because this one is related to our central measurement, flexible behavior. Because if they have repetitive restricted behavior, they might not be so flexible, right? So this is the idea, the rationale. So behavior rigidity or repetitive behavior, it is underpinned by cognitive inflexibility relative to healthy control, for instance. So this basically means inability to shift to different actions depending on the situation. So when the situation has changed, maybe because of the rejected behavior, they might not be adapt their behavior as quickly as possible as opposed to normal individuals, healthy populations, for instance. This is also related to self-control, inhibition control, as a psychological construct. So there are some evidence and literature. I'm just showing you here because I want to skip it. Too much words. So to investigate the flexible learning behavior in autism, we just use a task like this. There's the 80-20 phase and then also the reversal 20-80 phase. And if we want to look at the time theory of a task like this, we could imagine we are asking the individuals to work on the task, to work out the task repeatedly. So there are multiple trials, 80 repetitions. In the first half, the yellow one is the better one, and then in the second half, the blue one is the better one. This change is unannounced to the individuals, as I told you. So we didn't tell the participants there's a change. They have to find out by learning, by acting, and receiving the feedback. So essentially, there are things to look at. If at the very beginning, the first half, if they choose A, they receive a probabilistic punishment. So this is according to probability. 80% of the time you get a win. 20% of the time you get a loss. So if you choose A, occasionally, rarely you get a loss. But if you're a good learner, you should ignore that because you figured out already that choosing A is most of the time better. You just choose it, even though occasionally there is a loss. That's probability. This is because of randomness. But after the reversal, this occasional loss might become more informative. So after the reversal, even though this is unknown to yourself, you figured out already A is better, you keep choosing it, and then you realize that if you repeatedly choose it, you will get more often the loss. And then you might just wonder, what is happening here? Maybe there is a change already in the environment. I choose the previously better one. I do not get the intended outcome as before. So I get a lot of losses. What should I do? Maybe I change to choosing B instead. Also related to the previous talk. So we are talking about a lot of data, or maybe also this morning. I wasn't there, and also yesterday. So we wanted to test individuals in this learning task. And we cannot really only test maybe one person, 10 people. 100 is also kind of not too many. What should we do? One way is to use something called a multi-lab approach. So the same task is deployed in multiple cities, multiple labs in the world, but maybe at least in Europe. So here there is something called a longitudinal European autism project. It is a multi-center study across quite a few larger psychiatric centers in Europe. So we, in the end, have autism spectrum disorder individuals for about more than 300, and the healthy, typical developing individuals for about 250. And also, interestingly, we have the developmental stage data. We do not only have healthy young adults between 18 and 35 years old. We have children, adolescents, and adults. Not really adults, but kind of a younger adults spectrum, so that we have a rather full range of spectrum in terms of developmental trajectory. And this is with large collaboration with King's College London, England, and this is the core collaborator of this project, Daisy. Right, so we are asking the participants to do this same task, as you have seen quite a few times already. Right? You're familiar with the task, blue, yellow, and choose one, and you get a reward and see if there's a is to see if there's a change, and then you might need to change your behavior. So this is the task, you know how that looks like, and this is the real data from more than 500 individuals, just across all of the age groups, across TD, typical developing and autism spectrum disorders. This is nothing interesting, but I'm showing this one only to show you that the individual behavior across the age groups, across the clinical groups, they behave relatively according to the task structure, right? So they find out quite early on that the yellow one is a better choice, and after the reversal, there's a drop, there's a change of the behavior. And also, because we know the behavior, the environment has changed midway, but we also see there's a kind of a lag. So they do not really detect the change, the reversal immediately. They have to try out a few times until they find out there's a change in the environment. So here, this is the overall effect we are looking at. But looking at the overall behavior is not so much interesting because we want to see if there is a difference between the ASD, autism spectrum disorder individuals and the healthy individuals. We want to see that. And we also want to see if there is a change as a function of age, so children, adolescents, and adults. So this is what we did, and we look at their choice accuracy. As I told you, in this task, we could measure the choice accuracy, so how often they choose yellow in the first half, how often they choose blue in the second half. And we saw that across the two phases, this is the beginning, the acquisition phase, this is the reversal, the second phase, and on the x-axis, those are the age groups. And we have in red the autism, and in blue, in green, the typical developing individuals. Across all of these subgroups, the typical developing individuals, they are consistently performing better than the ASD individuals. So the blue one is better than the red one, as you can clearly see right from here. And essentially, this tells us that overall healthy participants are performing better than the ASD. That means they also detect the change better because especially this part, after the reversal, the healthy individuals, they found out the change earlier on so that they were able to choose the blue one more often relative to the ASD individuals. The second analysis is what I told you, something called the error, the mistake after the reversal. So only after the reversal, how often, even though in the environment, the blue one is the better one right now, currently, how often individuals are still choosing the previously better one, the yellow one. So in a way, they get stuck. Even after the reversal, if I'm still thinking, I choose yellow, I get a loss, this is about probability, I still choose yellow, I get another loss, this is about probability, I didn't really realize there's a change in the environment, so I get stuck. So this is the analysis. And if, let's say, the autism spectrum disorder individuals, they did not figure out the change effectively, they will stack more. That also means they will make more mistakes after the reversal. And this is what we see in red. The ASD individuals, they make more mistakes overall relative to the healthy individuals. I can tell you the result without modeling already. But then, as I mentioned, as also in the introduction, we're interested in the computational mechanism underlying it. So we applied a computational modeling to explain the behavior under a reinforcement learning framework. Because as I mentioned in the task, so you are presented with two choices, blue and yellow, right and left and right. You make a choice, and then you will receive the corresponding feedback, either a win or a no win or loss. And you will be going to use the feedback to update what do you think will give you a reward on the next trial. So this is learning, and this framework is best suited within the reinforcement learning framework. So here it is the individual make a choice, blue and yellow, and blue and yellow is kind of the environment, and the environment, blue and yellow, will return a reward back to the individual. So I choose one, A, yellow, to the environment returns to me a reward. The reward, from my perspective, this is observation. I will use the observation to update my belief, and then I will make a further further action to the environment, and so on and so forth, right? So here, the goal of a person or an individual here, or maybe an agent, however you call it, and the goal is to gain reward as much as possible and also avoid punishments using feedback-driven trial and error learning. And then the central idea here is to update what you believe is rewarding or not, using two equations. One, this is the Risch-Wagner model. The two equations, they are actually just together. One idea is that there will be something called a reward prediction error, which is the difference between what you get and what you expect to get. I think maybe this doesn't make sense. Let me explain that to you. So I give you two choices. You're about to make a choice between one of the two. In the very beginning, maybe you have no idea which one is better, which is worse. Maybe you think, well, in your mind, the value of option A and the value of option B is the same. They're equal. And then you will be making a choice between the two. Say you choose this one. Because you didn't expect anything by choosing this in the very beginning. You don't know what is there, right? You choose one, and then if, let's say, you get a reward, what do you think? You think maybe choosing this one is better, right? Because you didn't expect anything, but the reality tells you that this is better. So you want to increase what you think the value about this option is slightly towards the outcome. So this goes both ways. If you have your expectation, and what the reality tells you is that it's even better than your expectation, you will increase your expectation. And if, let's say, this is your expectation, what in reality you have is something worse, and then you will decrease your expectation. And this is something, I think that makes sense, right? So this is what these equations tells you, and essentially you are updating the value of the two choice options towards the outcome. If you think if you get something better than what you think, you will increase your, what do you think, the value. If you get something worse than what do you think, the value of the options, the value of the option in your mind is decreased towards the lower end. Good, and so this is the central part, but if anything is unclear, let me know. All right, all good, all makes sense? Okay, cool. So this is the central idea, and we are using that to model the behavior in our study. And we used that one, and also we had a few variants of that same model. So we add one more parameter to some part and one other parameter to some other part. I'm saying this very vaguely because it will require a lot more explanation. I just skip that. So in the end, we have 3 variants of the model derived from the one from the previous slides. And we want to see which of the model is the best one within each age group, also within each clinical group. So we have here the TD and ASD, we have here the age groups. So quite interestingly, regardless the meaning of the actual model, what that is, we found out that in children, regardless of the clinical difference, their winning model is the same, the yellow one. So the yellow model, this counterfactual updating, I can explain later if you're interested in. And here, also very interestingly, regardless of the TD-SD difference, in adolescents, the green model is the winning one. So the larger the model, the more evidence suggesting this one is the better model in that group. So for children, it's yellow, for adolescents, it's green, and for adults, that's the gray model. This is another one. This doesn't tell you anything. And we wanted to know, let's say, in this model, there is a free parameter. So this is called a learning rate. I told you something that if something is better, if the outcome is better than your expectation, you increase your expectation. And the increase of the expectation can be faster and can also be slower. And this is governed by a parameter called the learning rate, essentially the speed of updating your belief or the value. So the learning rate parameter is quite interesting in the sense that if, let's say, the winning model is the same, in ASD children, this model is the best. In TD children, this model is the best. If the model is the same, but also recall previously I told you the performance of the ASD individual is worse, right? If the model is the same, we could say, well, maybe kind of the cognitive mechanism is the same, but what is difference to explain the behavioral difference? So behaviorally, they perform a little bit worse. Why, right? So then we wanted to know how about looking at the learning parameter, the learning rate. If there is a difference in the learning rate that is able to explain the behavioral performance, what do we see? So indeed, that is the case for the learning rate parameter in the children group as one example. So the TD learning rate is lower than the ASD learning rate. So here you could imagine this is as the typical developing individual, their speed of updating is a little bit slower than the ASD. The way I'm describing that is also kind of a little bit confusing, I guess, because usually you would imagine typical or like healthy individuals, they are learning something faster. Some clinical individuals or clinical populations, they are learning something a little bit slower. What I told you is something different. It's the opposite. I told you from here, or at least from the data, is that the ASD individuals, their learning rate is larger than the learning rate of the TD group. So the ASD individuals are learning faster than the ASD individuals are learning faster than the TD individuals. Why? Right? This is very confusing in the very beginning. So to understand this, we actually also have to understand the model, how the model works, and according to different learning rate parameters. So what we did is something called a simulation. So we have our model and we have our task. So 80-20 and then 20-80 for 80 times. There is a reversal in the middle. We have the task. And we just ask our model as a data generating tool to simulate different behaviors using different learning rates from the full range from 0 to 1. And then to see, according to our task, what is the optimal learning rate? What is the best learning rate theoretically that will generate the highest behavioral performance? And we found out that in our learning task, the optimal learning rate is somewhere here around 20.2. And now that we have the optimal learning rate, we could place the learning rate of the TD individuals and ASD individuals in relation to, as opposed to the optimality. So not so surprisingly, you see the the TD individual learning rate is closer to the optimal point, and then the ASD individual is a little bit further than the relative to the optimal point. So only looking at the magnitude, this is higher, this is lower, doesn't tell you too much, unless or until you found out where the optimal point is, and then you will have to compare the result in relation to the optimal point. So then this makes sense, rather than counterintuitive. Right. So if you're interested, maybe just one minute to explain why a relatively learning rate is optimal in that learning task. It is because these equations I showed you, you could even reorganize it for representing the value at current trial t, for instance, as a function of the initial value. I told you at the very beginning, you think the value is the same for blue and for yellow. Let's say both of them are 0. And then it's getting updated. Some value goes up, some value goes down, for instance. This is the trial by trial update. I update my value from trial 2 to trial 3, and then from trial 3 to trial 4. But you could also imagine how could we write down the equation of trial number 4 as a function of the initial value. So this is what we do here to explain, to better understand how the value update works. And there is a kind of interesting term, and you don't know what that means. And the best way to understand something you don't know is to make a plot. So if you plot it, you could see that by changing this learning rate parameter, there are different color-shaded curves. And say when the learning rate is high, this one alpha, in darker purple. So when the learning rate is high, the weight of the current reward is very high, and whatever that is happening in the past, it receives a weight relatively close to 0. So this is close to 0, this is close to 0. And when the learning rate is low, 0.3 for instance, the weight of the current reward is 0.3, but whatever happened in the past is non-zero. So there is a remembering effect. You remember what has happened in the past. Translating that to kind of our understanding, what does this mean? This means if I received a reward in the last trial, I remember that sharply. I do remember there is a reward in the past trial. And past trial t plus 1, t plus 2, t plus 3, I forget what that happened. Even though, for example, I receive win, and another win, even though that's 5 times, I only memorize the most current one. And the consecutive wins in the past, I forget. So if, let's say, there is a lower learning rate, I have, for instance, also 5 consecutive wins. I memorize all of them even though each of them I kind of forget a little bit. But this is also maybe not a good example. Even better example is like this. I have 5 trials, 4 times of win in the beginning, win, and the most recent one is a loss. Okay, it's a loss. According to this construct, if I have a higher learning rate, even though I have 4 times of win previously, the most recent loss will give me a huge decrease in the value. And if I have a lower learning rate, the previous 4 wins, I will carry that out into my current understanding of the value, and then the most recent loss will not impact me so much. Okay? So the idea is like this. If the learning rate is very high, then I will only kind of memorize the most recent one, and I update very sharply. But if the learning rate is relatively low, I have a slower update. I memorize what is going on in the past. So back to our case, we have a rather stable learning environment. So 80-20 in the beginning and then 20-80 in the second phase is rather stable. And I could, if that is stable, I could be able to carry out what is happening in the past to my current understanding. And then that explains why a relatively lower learning rate is better than the larger learning rate. That makes sense? Kind of? Okay, good. Right, so that's essentially it. And those are more results for the learning parameters in the adolescents group, in the adults group. And there's no really time to explain that, but roughly they all show the same message. The learning parameter in the TD individuals is suboptimal relative to, So those parameters, they show the same message. The TD learning parameters, they are a little bit further towards the optimal learning rate relative to the healthy learning parameters, the same message. Right, so then with that example, I'm switching gear, well, not really switching gear, just going from the more concrete example to the more broader question in the theory, in the field of computational psychiatry. So the example I give you is to use reinforcement learning models, for instance, to explain flexible learning behavior in autism spectrum disorders in relation to healthy participants. Why the ASD individuals behave a little bit suboptimally because of the suboptimal learning rate in that case. So using computational model is kind of really insightful, at least to my understanding, to explain some clinical differences that usually are very interesting. So this is a field, it grows really fast. It started only like 2010, for instance, roughly. So this is to use, this is a new and rapidly growing field which seeks to characterize mental function and, more importantly, dysfunction in clinical populations in terms of computations, modeling, for instance, at multiple scales and brains and behavior and genetics. And so this is very rapidly growing and highly multidisciplinary field. This also, again, relates to the previous talks. There's anxiety and something like fear, I guess, sorry, related to like the climate debate. There are papers about it every year, and this is new, but you can also date it back to something like 40s. So as early as 1940s, this is the idea to explain something like here, mental disorder functioning, and here disorders like malfunctioning in terms of computations, in the computational perspective, where the mind goes wrong in clinical populations in relation to healthy populations. What I showed you, there are multiple approaches to conduct computational psychiatry research. What I showed you in the previous example is here, a data-driven approach, theory-driven approach. We have a computational learning framework, the reinforcement learning framework, if you imagine that is a theory-driven framework, that is a learning theory. From there, we could explain how difference happens within two groups. But there are also data-driven approaches like machine learning, classifications, use pattern recognition, natural language processing. All of them are also helpful in terms of understand mental dysfunctions. And also now in the modern era, we have a lot of digital data. We have digital data from, for instance, Facebook, Twitter, and like the Facebook traffic data. And all of them are quite pretty useful for us to understand interesting behaviors. Right. This is only like a short introduction of computational psychiatry, only to bring that to your horizon, so that in your future study, if you are interested, you could look into that part. And now we have a very last part of the talk, which is slightly more practical. So I will introduce you something called age-based DM. This is an R package. Now it also has a Python interface if you are more a Python person. I showed you using reinforcement learning to understand behavior is interesting, and I like the idea of modeling, but actually if you look at literature, some of them, they are confusing. It doesn't make so much sense in the very beginning. What you can do, right, if you want to apply these approaches. So what we did is like, well, let's look at this one example. The models, at sometimes they can be confusing. In fact, what we did, this is another paper that we had. So we have a social learning task. Essentially, it's not so, I don't want to explain everything to you. Essentially, people integrate direct learning experience and social learning experience into their own decision-making process. That's it. And this is a model structure, and those are the actual models, but you can't really tell computers the equation to run the models, right? You need to write computer codes. So then those are the corresponding computer code of the same model, all of them, they are equivalent. And you could imagine writing this is not so straightforward to begin with. And let alone we are doing Bayesian inference, this is another layer of complexity. So we wanted to lower the barrier of people who are interested in applying this approach in their own research. So we had developed a package, ARC package, so the age-based DM, hierarchical Bayesian modeling of decision-making tasks. Hierarchical here essentially means we do not only consider, for example, if we recruit 40 participants in one psychology research from University of Graz, for instance, they are individuals. If we constrain our population to be healthy young adults, usual case, possibly, very presumably, they come from the same group, they are from the same group. And the usual approach doesn't really consider their commonalities among the individuals, but the hierarchical approach considers that there is a higher level group distribution, the assuming underlying group population where the individuals are coming from. So this is the hierarchical approach. So all of the learning models are implemented in a hierarchical structure. And also, like in the introduction, I had my teaching materials online on YouTube. If you're interested in this, so feel free to check that out. So also the paper, if you are interested in. Let's see, in our particular case, what is done, right? So we have the task. You have seen this multiple times. So reversal learning in acquisition phase and reversal learning in reversal phase. You could, if I give this task to you, if you happen to study psychology, and you can ask yourself what you want to measure, what you want to study, what you want to analyze. So you could imagine the data might look like this. So you have your participants, and you have your trials. Each person is repeating their trials 80 times. And each time, what are the data? The essential data just are two variables. One is the choice, the other is the outcome. So blue and yellow, which one you choose? Blue, okay, you get a reward, okay, then you get a reward. So this is the data. You choose blue, you get a reward, choose blue, you get a reward, choose blue, you get a reward. And maybe there's a punishment coding. So those are the data. So from the data, what we can measure, we could already measure choice accuracy, as I told you. So choice accuracy doesn't depend on the model. You don't need a model to analyze choice accuracy. Accuracy here means in the beginning, how often they choose yellow, then how often they choose blue in the second phase. Now, interesting part is why they make the behavior. If they choose blue, they get a win, they repeat their previous choice. Why they do that? There's a reinforcement learning framework and model to apply. Yes, so then that's how that will go about. In a few slides ago, there was a color coding. So I told you in children, the best model is yellow. In adolescents, the best model is blue. And in adults, the best model is gray. I didn't tell you what they are, and those are what they are. The yellow one, this is a counterfactual learning model. And the green one, this is the reward punishment model. And the gray one, this is the experience-weighted attraction model. Without going into details, they are different. So you see here, without this, the first line is the core model I showed you, but this one updates the value of both choice options. And if you also think that the updates, this is your expectation, this is your outcome, you update, right? People might update in an asymmetrical manner, such that when they receive a reward, maybe they update faster, and then when they receive a punishment, they update slower, or maybe the other way around, doesn't matter. We just give additional degrees of freedom to quantify the learning in reward context and also in the punishment context. And here is another one that's a little bit more complicated. I will skip. Right. For the actual model fitting procedure, in your study, maybe you've heard about that. To fit a linear regression, you will have two parameters. One is the slope, the other one is the intercept. You use maybe something called a least square measurement to get the best combination of the slope parameter and then the intercept parameter that gives you the minimum square of errors. There's another approach called maximum likelihood. So you get a set of parameters that returns to you the maximum of likelihood. So those are the best parameters optimization problem. And here, the approach we have been using is called the Bayesian approach. So the central idea is to use sampling procedures using Markov chain Monte Carlo. Don't really try to memorize all of the details. This is too much. I know this is just to show you where these things come from. So Markov chain Monte Carlo, there are the multiple methods, and it's not even interesting. But the interesting one is here, we are using something called a STAN. So this is a software package. This is the underlying computer programming language that our package, HBaseDM, based on. So our package is RPack package, but the underlying is STAN language that does all of the Bayesian sampling and parameter estimation. Practically, this means we have R. If you are using R, this can be Python as well. So you have your experimental data, you organize your data in a nice way, and so that STAN can recognize. You parse your data from R to STAN. STAN does the heavy work, Bayesian sampling, Markov chain Monte Carlo, blah, 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 something like that, and then return the result back to you in R. And those is the platform. You could do plots, you can write down summary statistics, draw statistical inference, and then write a paper about it. Right, so here you could imagine we have a main file that does all of the data preparation, and here in the STAN side, we have multiple models. We have like the color model, yellow model, green model, gray model, whatever model, different models. And also we need to do model comparison to find out which one is better, which one is not better. Great. I will try to give you a conceptual walkthrough in the sense that without showing you the program interface, just really conceptually how to do this kind of analysis if you are interested in. So we have the raw data. I showed you already. So you have the trial, subject, choice, and outcome. Those are the raw data. 300 individuals, ASD individuals, and 200-something individuals of the TD typically developing. Those are the raw data. And you prepare that in a way that is easy to be recognized by the STAN language. So you can write a function, if you know how to write a function in programming languages, to write a function to prepare the data, give the raw data as an input, then you prepare the data, then the output is a nicely prepared data. PRL here means probabilistic reversal learning task. And then we could do behavior analysis. So analyzing the choice accuracy, as I told you, to analyzing the choice accuracy, you don't need a model. You just count how often they choose the better option in both phases. Those are the behavioral analysis. And then comes to the model. We have multiple model candidates, model 1, 2, and 3. each of them, they are written in the Stan syntax, in the Stan language. I will also try to show you a little bit later. And then there is a function to try to combine them because model itself doesn't do much. We want to fit our model to the data. So to see how the model fitting goes together and then to see the parameter estimates, the learning rate, for example. So we want to see to run models according to which model we are giving in and also according to which group they belong to, either ASD individuals or like healthy individuals. And the ABC here means adults, adolescents, and children, age group, right? And there are something else, a little bit more practical consideration is that maybe the model fitting is not working well as intended to begin with. Maybe you have to try multiple times. Those are called model diagnosis. So it's like if you go to a doctor, medical doctor, and you have some symptom, and the doctor tried to give you some suggestions and some diagnosis, but maybe in the beginning it's not precise. The doctor needs more information, more symptom, more your medical taking history to understand you as a person, so that there will be a better diagnosis. Here's the same. You will diagnose the model to make the model better. So the doctor will diagnose you to make you more healthier. Right, though this is very detailed. It's not so much important. So essentially, there are more steps, and then eventually, you can write a paper about it. To begin with, you can think about it like you have some measured task, and you do some cleaning. So for example, also some participants, maybe they didn't press the button in time, and for more than 50% of the time, this can be discarded because the quality is relatively low. So you clean up the data and then do some analysis without the model. This is called model-free analysis. And then you go to the model fitting part. We have model 1, 2, 3, fit it to each age group, to each clinical group, and then find out which is the best. So for example, the second one in like bolder frame, that is the better one. And then there are some further analysis. I didn't show you this, but this is rough idea. Okay, great. To summarize, so computational, this idea can be dated back to 1930s in psychology, at least. The idea is never new. Maybe this is new to you. In your bachelor study, you never heard about this, but this is actually never new. So don't let that fear you. There are some equations, but you can always run simulations to understand what is going on. Like in the agent-based model, the number of sheep and wolves, do some simulation to see the dynamics of all of the interacting agents. And the Bayesian framework is rather reliable and better than traditional model fitting approaches like maximum likelihood, for instance. There are some more classical works. This is what your bachelor study is about. So if you are studying in bachelor studies, you learn a lot of classic psychology papers from 70s, 60s. They're gold. You dig into that, you always find interesting questions, rather than looking at a paper from me 2 years ago, for example. Yeah, and right. So another kind of thing we want to talk about is one reason to come to this summer school, spring school, whatever training opportunities, like you can seek to meet new people and then to find out if you can do something interesting all together. And right, those are some learning sources. Slides will be distributed later on from me, from other people, from books, from different places. So my contact information, too fast. Yeah, that's not important. That's it. So thanks so much for your attention.